Okay, welcome everybody to Access Distinguished Lecture number 80. Today I have the pleasure to introduce Dr. Vijay Srinivasan from the National Institute of Standardization and Technology from the United States. Srini has a long distinguished career. He would not be a typical distinguished lecturer coming from mechanical engineering and production, but it fits very well into the interest we have here at KTH into systems engineering, which cuts across many different disciplines. And I'm happy also to see that we have some in the audience coming from other area. So Srini has a career, I think 26 years at IBM. And then since 6 years being with NIST, where he is basically heading systems engineering. He has also many other positions. For instance, he were teaching at Columbia University for some time. I won't go through the long bio here, but let me just mention that he is also a fellow of the American Society of Mechanical Engineers. He's fellow of the American Association for the Advancement of Science. He's visiting us for this year. Next week, sorry for this week. Next week, we're organizing a workshop, Access and LCCC in Lund on model-based systems engineering, where also Srini is participating. But today we are very much looking forward to your lecture. So please, Srini.
Thank you, Kalle. Thank you very much. It's nice to be back at KTH. So what I wanted to do today is to talk about some of the recent interest in manufacturing. In fact, I should motivate you why we should be talking about manufacturing in a seminar series such as this, and that should become very clear to you very quickly. And also the journey that we have taken, that is a historic view of how we have managed to get model-based engineering to the benefit of advanced manufacturing. So that's going to be the main topic for my talk today. So why are we talking about manufacturing? Well, there's a lot of interest, a lot of talk about manufacturing right at Sweden, and you all know that because some of you contributed to this strategic vision or the strategic innovation strategy, the agenda for production in Sweden. So you see that both KTH as well as Chalmers along with many other leaders participated in creating this particular document. And in fact, out of this document also came a vision called the Production 2030. So the vision states that by the year 2030, Sweden is the primary choice for sustainable production. Now, if you look at what are the contents of this particular Production 2030 vision, is that cognitive automation, implementing research in industry, and sustainable production. These are three major parts of this particular vision. And in particular, if you see the gentleman holding a green leaf at the very right of your chart here, well, he is Björn Johansson. He is a professor of production engineering at Chalmers University. I know Björn quite well because he spent a sabbatical year at NIST with us, working with us on many of the production engineering oriented standards. Now, I also came to know about this Production 2030 and the Made in Sweden campaign through a delegation of people, including Björn, who visited United States last year, and they also visited NIST. The reason why they did that was that in the US, again, you have a Made in America strategy. So this is the so-called next generation of innovation strategy, and starting nearly 5 years ago, a high level of people worked on this particular area and came up with a series of policy papers. And these are publicly available. They come all the way from the White House, so they have a lot of visibility. And many in Sweden have also been following, along with many other people around the world. So many people have also come to the United States to talk to us about what's going on, because this is a very high level interest even among the policymakers and also in the public-private sector. Both the industries as well as the universities and the government agencies are very much interested in looking at how they can spark innovation in the field of manufacturing. The basic fact is that you have to make things that the others want to buy. That is the only reason, that's the only way in which you are going to have a trade, and that is the only way in which you are going to have an economic prosperity. So that's why many countries are interested in doing this. And Sweden and United States are not alone. In fact, in the US, in addition to coming up with these policy papers, we also have what is called a National Networks for Manufacturing Innovation Institutes. So what we have done is that we have started creating a fairly well funded institutes in very specific areas such as additive manufacturing, power electronics, lightweight metals, digital manufacturing, advanced composites. So we already have about 5 such institutes, and we are creating more as a part of a network of manufacturing innovation. Now each institute is funded by public private partnership. What I mean by that is that the government puts in some money and then it is matched or exceeded by local governments and private sector. So each institute has more than $100 million worth of funding together, the public private partnership. Each institute has that for a period of 5 years. So, and we are also planning to have more such institutes to join this network. So this is the level of interest coming from fairly high level to spur or spark the manufacturing innovation in manufacturing. And as I said, it is not just in Sweden and United States that you have such interest in innovation in manufacturing. In Germany, you have the Industry 4.0, and India has the so-called Make in India campaign. So there are lots of countries that are interested in the manufacturing. So that is the reason why I'm also here to talk to you about how model-based engineering is helping manufacturing in a very big way. So the thesis of my talk for the next 50 minutes or so is going to be that the models are very critical to manufacturing, and I will tell you a little bit about what do people mean by models when they do manufacturing. The second is that we have come a long way in the so-called 3D model-based engineering for manufacturing. This is the 3-dimensional geometric models and how they are used in manufacturing. We have come quite a long way, and I will give you a little bit of the progress that we have made in this. Then finally, I would observe that we can apply the lessons learned from the 3D model-based engineering to other areas such as the model-based systems engineering and a few other things too. So I will say a few things about the lessons learned from what we have achieved and what we can achieve in the future moving on to model-based systems engineering. So let me start with some pretty well-known result, but a pretty old result. Let me start with the very classic Plato's theory of forms. Now this is studied quite extensively in the philosophical as well as some literature classes, but there are some passages from Plato that are very relevant to modeling and manufacturing. So that is the surprise. So even about 2500 years ago, people were thinking about models and manufacturing, and I want to bring that to your attention. So there is one particular writing of Plato, it is called the 7th letter of Plato. So what I am going to do is in the next 3 slides, I am going to show you some portions from the 7th letter of Plato, where he talks about the theory of forms, and I will try to show you how even then people were talking about or thinking about models and manufacturing. And by the way, the history behind the 7th letter is very interesting. It's a very long letter because Plato got involved in some political scandal in Sicily. So he was trying to explain his involvement in that political scandal, but in the middle of that letter, he gets into the so-called theory of forms. So what he says is that, so in the 3 slides, what I have also done is that on the left, I have given you the original text in Greek because I know there are people like John Barras in the audience. In fact, I have shown this slides before to him just to make sure that the translations are not corrupted, that actually the translation is faithful to it. So what Plato says is that to know about anything, there are 3 things to start with. And then there are the 4th and the 5th things that he will talk about later, but there are 3 important things about to gain knowledge about anything. And he says that the 3 things are, the first is the name itself, the first is the name, second is the definition, and the third is the image or some concrete manifestation of that particular idea. Okay? So those are the first 3 things, and then there is this knowledge and intelligence about it that comes as 4th and the 5th. And then he goes on to say that, let me explain it to you using an example, because that's the best way to illustrate a particular idea. And thankfully, the example that he chooses is a geometric example. So he says that, let me take the example of a circle, and then he says that first there is the name called a circle. And second, you have a definition of the circle. For example, the distance from the circumference to its centers everywhere is equal. So that is the definition of that particular circle. Then he goes on to say, then comes the third. So either you can draw the circle and erase it, or you can turn it on a lathe and break it up. So this is the sort of the manufacturing example that Plato brings up as the sort of the third element in the theory of form. But he goes on to say that, look, what you turn on a lathe as a circular object is not the same thing as a circle, but this object will refer to it. So the circle is the model. So there is this definition of a type called a circle, and then there is there is the definition of what exactly that particular mathematical definition of what that particular circle is, and then there is a manufactured instance that is supposed to be a circle. Then he goes on to say in the same letter that no manufactured circle can ever be perfect. That is, no manufactured circle will have the property that all points on its circumference are equidistant from its center. Okay, that's the reality. There is no real object, that is, no manufactured instances such as this will possess this ideal form, but we still need to have the ideal form as an idea. That is the model, mathematical model. So it starts all the way from the thinkings and the teachings and so on of the ancient Greeks. And the next he talks about a few things that I project in this particular slide. Then he talks about the knowledge and intelligence about this is quite separate from them, quite understandably so, because just because you know the name of an entity called a circle and its definition doesn't give you all the knowledge and information about it. You have to learn other things. What is the circumference? What is the area? And what are the properties of these circles in relationship with these so many other things? So there are other things that you have to add to it. And I will tell you that strikingly, many of the things that we do in model-based engineering for manufacturing follow many of the fundamental things that we learn from the theory of form, because as I will show you, type definitions are very important. For the data models, which are very key for computerized representations, for machine readable representations of them, the data model definitions are extremely important. So that is what you mean by, in the previous slide, the name of the entity and the definition of it and a concrete instance to which refers to this particular model. Okay, so this is the very quick introduction to how the ancient Greeks themselves were thinking about model-based models for manufacturing in that. Now, there are two major axioms that govern, which are derived roughly from this. The first is definitely derived from some of the Plato's works and other things, is that these are the two major axioms in all of manufacturing. There is no escape from this. The first is the axiom of manufacturing imprecision. What it says is that all manufacturing processes are inherently imprecise and they produce parts that vary, meaning that you can never manufacture Platonic ideal forms, even though you will refer to the Platonic ideal forms in your models. Now, there is no escape from it, because that's the only way we can do how to model geometric entities. But any manufactured object will never be that. Therefore, in manufacturing, it's very important that you specify what is the allowable variability in your manufactured part from the Platonic ideal form, which is the model. So this is key and fundamental to all of manufacturing. The model has the Platonic ideal form in geometry, but remember, you can never manufacture it according to that perfection, so you always have to specify the allowable variation, and then you have to control that in production. The second related axiom is that it is the measurement uncertainty. You will never be able to make any measurements perfectly. There will always be some uncertainty associated with that measurement. Now, I also state this slightly from an authority, because I work for the National Institute of Standards and Technology, and in the United States this is the highest authority for measurements. So even the highest level accurate measurements that we make in the country, in the United States, whenever we make them, we always specify the uncertainty associated with it. That's why in every experimental work that is reported in scientific literature, you see an error bar, because you can never measure anything perfectly. There is always a measurement uncertainty associated with it, and it is an absolutely important scientific and engineering practice that you report the uncertainty associated with your measurements. Otherwise, we won't believe you. That's basically what it is. You have to measure with that. Now, these axioms might look independent, but in reality, they are realized. In every instance that we have in reality, we have to deal with both the manufacturing imprecision axiom as well as the measurement the uncertainty axiom. Okay, so we have dealt with some of a little bit of the history from the ancient Greeks, but now let us fast forward and go to the time between the American Revolution and the French Revolution. So why is this particular period important? Because in 1785, this is the time between after the American Revolution had taken place, but before the French Revolution, Thomas Jefferson, who was a leading figure in the American independence, and he is also a brilliant man, and if you have studied anything about what Thomas Jefferson had done, he is a remarkable man who has dabbled in so many areas and done very well in them. And he was an ambassador to France during that particular period. And then he wrote a letter at that time to his friend John Jay, who later became the first Chief Justice of the United States. And he wrote a letter in which he was talking about a particular manufacturing process that has been invented in France. And if you read it, it makes it very clear. What he says is that the construction of muskets, an improvement has been made in the construction of muskets. A musket is the long gun, the shoulder fired gun. And he says that it could be of interest to the United States. So what is it? It consists in making every parts of alike so that they belong to anyone. So supposing it might be useful to the United States, I went to the workman. He presented me the parts of 50 locks. A lock is the firing mechanism in the musket. And he presented me the parts of 50 locks taken to pieces and arranged them in compartments. I put several together myself, taking pieces at hazard at random as they came to hand, and they fitted in the most perfect manner. Then the punchline: the advantage of this when arms need repair are evident. So what he is talking about in this particular case is interchangeable assembly, interchangeability of parts in an assembly. So when something goes bad, which always does in the field, in the field, you should be able to quickly replace the bad parts with the good parts. Your life may depend upon that. So what he observed in this is the first instance, big instance of in the military field, interchangeability of parts in an assembly. Before that, bulk of the way in which engineering was practiced was the so-called artisan manner, that is file and fit. You make each assembly as a separate entity. You produced individual parts and you filed and fitted them together, and it will work for that particular assembly. But you can never take a part from one assembly and put it in the other and hope that it would work. Now this sparked a whole bunch of revolution called interchangeable manufacture. And in fact, interchangeable manufacture is the basis for much of the proliferation of mass production. Because without interchangeability of parts, you cannot have division of labor, and you cannot have the mass production. Things produced, parts produced in parallel, and then you bring them together and you assemble them. So the one that Jefferson was referring to was the 1765 Systems Gribois, which was invented in France and developed there. Then 1808, Eli Whitney in the United States, 1803, Marc Isambard Brunel in UK, and then in the 1820s, the small arms manufacture of the United States was very much governed by the so-called American system, and I will say a few things about it in the next slide. It is all about how do you make interchangeable parts, how do you do interchangeability in assembly. And it then spread beyond the armory, that is beyond the military application, to clocks, sewing machines, reapers, bicycles, and so on, ultimately ending up in the Henry Ford's automobile assemblies in the early part of the 19th century. Now, as I talk about these things, I know that many of you are experts in electrical engineering, systems engineering, and so on. What I would like you to do is to think about the connection between some of the concepts that have evolved so far to what we are also thinking about in software and electrical engineering and so on. So some of the things are, you see, when we talk about assembly, you should also think about how these things are architected. and what is the modularity of the various components that get into this architecture. And when I talk about assembly and putting these things together, also think about the composition. How are you composing the various elements that you are modularizing in whatever field that you are working in, whether it's electrical engineering, software engineering, or whatever it is. The modularity, the compositionality and composability of these things, all these things are very parallel to what we are talking about. So interchangeability in assembly is very similar to worrying about composability of various components that go into a system. So that's the interesting connection, and we can draw a lot of parallel from the past. So let's talk about the so-called American system. What was this American system? In the sort of the mid 1820s, in the United States particularly, people developed this manufacturing process that can ensure the interchangeable assemblies, interchangeable parts in an assembly. What does it entail? Well, they use the so-called jigs, fixtures and gauging system, which are called rational. Because why is it called rational? Because it is rational because it is always with respect to a model. Because without a model, the system is not rational. And let me explain to you what I mean by that, by the model, always reference to a model. Think about producing many parts. So if I say that part A is close to part B, B is close to C, C is close to D, and so on and so forth, that is, you are only comparing with each other. By the time you go to Z, A may not be close to Z. Do you see what I mean? Okay, the transitivity is lost if you are merely comparing it to one another. But the transitivity, which is very important for interchangeability, that is, if A is interchangeable with B and B is interchangeable with C, then A better be interchangeable with C. So the transitivity is maintained only if each one of them are made very close to a model. Okay. Now, in those days, the way in which they achieved these models is a very precise machining of the so-called jigs and fixtures with which every part is manufactured. They also had, for measurement purposes, gauges, the gauging system. Now, I have to mention that one of the persons who contributed a lot to the standardization of gauging for measurements, which is very important for this type of American system, later on was Carl Johansson, with the Carl spelled with a C, Carl Edward Johansson from Sweden. And in fact, he is very well known for his gauge blocks. He is considered to be a pioneer in precision. He worked with Henry Ford in the 1820s, and his gauge blocks are affectionately known as Joe blocks, and they are used, even today people use the gauge blocks in the shop floor. So all fixtures are designed with respect to the model. Gauges for inspection were also made based on the model, and this is the only way you can get away from the file and fit artisan practice that was prevalent before. And you cannot do mass manufacturing with the file and fit system. As Henry Ford observed, in mass production there are no fitters. You just bring these components and they better assemble. You cannot be filing and fitting on the assembly line if you want to maintain the mass production. All right, so while all these things were going on, so people were developing all the jigs and fixtures and gauges with respect to a model, but people did not document what that particular geometric model was. But the engineering drawings started developing, and the standards for the engineering drawings started appearing in the 1935. The American standards started in 1935. The ISO standards for drawings started after World War II. I am sure that if you research the Swedish history, maybe the drawings in Sweden also started around 1935 period, but they all gathered together and then to have an international standard for drawings under the ISO umbrella, but after the Second World War. Now, initially the drawings did not carry information about the allowable variation, which is called the tolerances. But pretty soon after 1935, the subsequent releases, the drawings also started carrying not only the dimensions but also the tolerances, because that's extremely important for manufacturing purposes. But the three-dimensional models, not the 2D drawings, but the three-dimensional models with the dimensions and tolerances first started appearing in the mid-1990s. So roughly 20 years ago, that's when we started having this dimensions and tolerances. So what is the whole purpose? The whole model-based 3D engineering for manufacturing, its goal is move away from drawings that look like this with the parts with a lot of annotations that you see here, which are the dimensions and tolerances on them, move over to 3D models that you see here, where you do see the annotations of dimensions and tolerances, but since these are models, these are not merely annotations that only human beings can read. They are also computer representations in the form of entities, attributes and relationships that are captured in a schema. So these are three-dimensional geometric entities with detailed feature information, and each feature can have attributes and relationships that carry this dimensions and tolerance information. So what I will say is that what we are able to achieve right now is not only the human readable presentation, which is very important, but also the machine readable interpretation, the representation underneath of that. The machine readable representations are extremely important for further automatic processing of these things. Okay, now 20 years ago, as I said, around the 1995, this is one of the first instances. This is from a system called a CATIA, which is developed by Dassault Systems, and it was marketed by IBM at the time. So this was one of the first instances where a three-dimensional solid geometric model had all the dimensions and tolerances that you see on the right hand side on the 3D models as opposed to 2D drawings. But of course, at that time, this information, that is the internal representation of this information, was proprietary in a proprietary format. You need to have access to this particular CAD system in order to access that. But what we have done is that in the last 20 years or so, we now have an ISO standard. It was just released last year, where you have the standardized representations for this type of the dimensioning and tolerancing information in the new standard, and the standard itself is called Managed Model-Based 3D Engineering, which is kind of interesting because how the language develops. We have been talking about model-based systems engineering for about the last 10 years or so. Now you see in a particular field, the model-based three-dimensional engineering has gone to a stage where we are able to have an ISO standard. Now many of the PLM systems, that the product lifecycle management systems that have all the 3D geometric models and so on, they are now implementing, and you can export files that are consistent with this particular standard. So you can have a save as step file that can carry this information, not only for the human readable presentation, but also the computer readable representations, as I referred to. Okay, so I have quickly covered quite a bit of history, how things progressed from the early Greeks to 2014, where now we have an ISO standard for some of these things. But let me get a little bit into some of the technical details. I don't have time to get into a lot of technical details, but I'll give you some glimpses of technical details. So as we were making progress, it turned out that to go from the world of 2D drawing to 3D models required that you actually pay attention to the underlying mathematics, and you come up with the proper theoretical foundations for some of the ideas so that you can develop your data models with a great deal of confidence. So I will give you some examples of the role of congruence theorems in the so-called dimensioning, because I usually ask this as a part of my teaching in my class. I ask the students to draw a triangle, which is one of the simplest objects, geometric objects you can think of, and I ask them to dimension this triangle. And by the way, while you are dimensioning the triangle, can you also parameterize this particular triangle? So the students try many things, and some of the successful ones that I am showing are the what I am showing here. These are not the only way to dimension a triangle, by the way, but these are some of the successful attempts to dimension a triangle. Now, why do I say that these are successful or these are correct way to dimension a triangle? Not because I just feel so, but there has got to be some theoretical reason why I say that these are correct ways to dimension a triangle. It turns out that the Euclid's congruence theorems, the side angle side theorem and the angle side angle and the side 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 theorem that you see in Euclid support the claim that we just made, that these are valid ways to dimension a triangle. So this is a basic motivation. In fact, there is a whole theory of dimensioning and parameterization of geometric objects that is based upon the congruence theorems, starting all the way from the very basic ones that I showed here. There are a couple of interesting lessons to learn from this, because parameterization, parametrics, constraints and so on are very important to many disciplines, not just to geometry, but they are very many disciplines, but we can learn a lot from geometry. The first is, you notice that there is more than one way to parameterize or to dimension an object. That should be clear to you. There is more than one way to do that. But whatever way you use, you need only 3 parameters. So that's why the triangles are said to belong to a 3-parameter family of geometric objects. You need only 3 parameters for triangles. The other things that you will notice is that the moment you put down numerical values for these parameters, you are constraining this particular geometric object. So this is sometimes called the dimensional constraints. In fact, you can create an entire complex geometry by specifying some dimensional constraints on the geometry. And there are now very sophisticated constraint solvers, the geometry constraint solvers or dimensional constraint solvers in the market, and they have been in the development for over 3 decades now, and all the major CAD systems successfully use the dimensional constraint solvers in them. So it's very interesting that in one particular domain the field has advanced quite a bit, because this is a discussion that I have with many of the other researchers in other fields, because they all want to do constraint solving. So in one field at least, we have quite a bit of the wealth of research and research which is already implemented in major systems that people use for dimensional constraints. The next thing that I want to talk about is the role of classification theorems in geometric relationships. So the way in which I try to describe this relationship, the geometric relationships, is that if I take a very complex object, a very complex 3-dimensional object, and I ask you how many degrees of freedom do you need to position this particular complex geometric object with respect to your external 3-dimensional coordinate system, you will say that you need 6 degrees of freedom, right? 3 for translation and 3 for rotation. But if I ask you how many degrees of freedom do you need to position a perfect sphere in a 3-dimensional space, you will notice that you don't need 6 degrees of freedom to position a sphere, because all you need are 3 degrees of freedom to position the center of the sphere with respect to the coordinate system, because the rotations are irrelevant, because when you rotate the sphere about its center, it remains invariant. So the sphere possesses the rotational symmetry about its center. So the symmetry of an object has a very strong role in determining how many parameters that you need for relating one object to the other object. So let me take it one step further and ask you, how many parameters do you need to position a perfect sphere with respect to an infinite plane? The answer is you need only one, the distance between the center of the sphere and the plane. The reason is the plane also has symmetry. As you move it along, it remains invariant. So the invariant nature of the geometric object with respect to motions, which is related to the symmetry of this particular geometric object, has a very strong influence on the relationship between geometric objects with respect to each other, the relative positioning of one geometric object with respect to the other. So engineers have understood that, and for centuries they have had engineering practices by which they will specify these things as the dimensions and then carried on with it. But what we needed to do was to do a proper classification, and it turned out that there are only 7 classes of continuous symmetry, and the ones that I have listed here, the spherical, cylindrical, planar, helical, revolute, prismatic, and the more complex, the general ones. These are the only 7 classes of continuous symmetry, and you can prove this rigorously, and we have done that about 20 years ago. We rigorously proved this using the connected Lie subgroups of the rigid motion group, the R3SO3 group. So there is a very elegant and very rigorous mathematical proof that you can give to the classification of the symmetry, continuous symmetry of objects. Along with that is, you see the simple replacements, those that the sphere can be replaced by its center, the cylinder can be replaced by its axis, and so on, for the relative positioning purposes. So, there is a rigorous proof on how we can do this substitution, and what it has done is that it has given a good deal of theoretical rationale behind quite a lot of the engineering practices, and it also opened up the new ways of doing data models, knowing that there are only 7 classes of symmetry that you have to deal with in the data models. So, the completeness of your data models can be proved, and the proof is traceable to such classification theorems. Now, I also know that I am speaking in a Linnaeus Center. So, as you know, Linnaeus is very famous for classification, and I will say a few words about it. I was not trained as a classification person, but I stumbled upon the importance of classification as I was trying to do a computer based models for manufacturing. It turned out that doing such a classification is extremely important. And one of the things we observed as we were doing the classification is some of the types of constraints that you come across in manufacturing or in geometry, such as incidence, that is coaxiality and concentricity. Coaxiality is 2 cylinders having their axis on each other, the same axis. Concentricity is 2 spheres having the same center, and so on. So, coaxiality, concentricity, which are incidence relationships, and then parallelism and perpendicularity. These kept showing up as very important geometric constraints that the designers needed to maintain, and the manufacturers have got to control these constraints in their objects. And it turned out that there is also a classification, very elegant classification, that gives us the reason as to why, because there is this hierarchy of groups from the group theory. So, projective transformation, affine transformation, isometric transformation, and the rigid motion transformation. Each smaller one is a subset of the subgroup of the other one, and it is a rigorously provable one. All of them are part of the general linear group. And when you look at it, in each group certain things are preserved as invariants. So, in the projective transformation, the incidence relationship is preserved. What it means is that if you have a sphere that is tangential to a plane, under projective transformation, the sphere may become elliptical, but the plane remains the plane, but the plane will be tangential to the ellipsoid. So, the incidence relationship is preserved under the projective transformation. Affine transformation preserves the parallelism. Again, you may shear them, but the parallel planes will remain parallel. Isometric transformation preserves the angles, but the so called rigid motion transformation preserves chirality, that is, the right handed screw will be a right handed screw, whereas under a pure isometric transformation, a right handed screw may be transformed into a left handed screw. As you know, they are not interchangeable. Left handed screw is not interchangeable with the right handed screw in that. So, again, by looking at the group theoretic basis, you can see why certain constraints have a higher level of authority or higher level of classification. These are the basic geometric constraints, and they have a great deal of influence on how you position things relative to each other. So, with this, let me say a few words about the lessons learned from the 3D models for manufacturing. The first point is that it turned out that the congruence theorems and the classification theorems provided much of the needed formalism, because before that we had quite a lot of very good practices that engineers had, and they were the basis of the engineering drawings. But as I said, when you want to move to the 3-dimensional computer representation, you need to have the entity attribute relationship models for all these entities, so that you can do the computer representations of them. And also you developed algorithms for the constraint solvings and so on. So, to prove the completeness of the data models and the correctness of the various algorithms, we had to do some of the formalism that I showed here. But once we have this formalism, then we have very solid foundation for the 3D models, the computerized models that we developed in that. Now, I just want to sound a cautionary note against the informatics hubris. What I mean by that is, there is a tendency in some of the software engineering and computer science to assume that just because we know a little bit about abstractions and formalisms, we can automatically do that by just using those information. it turns out that you also need to know a lot of domain specific information here. So, in this particular case it is geometry, mechanics, manufacturing. So, you have to know a lot of domain specific knowledge. So, that is why one of the things that I do these days is whenever I talk to domain experts, I very carefully listen to the various entities that they are classifying in their domain, and I ask them, do you have a classification theorem? Because there are not that many. In fact, if we are lucky, if we have a very carefully researched catalog of types in many other fields. Only in a few fields I have seen rigorous classification theorems. Not that they do not exist, it is just that I do not know that. And if we can really find those classification theorems, I feel that we can benefit a lot for building models for them. So, this is one of the lessons that I painfully learned. As I said, I was not born or brought up as a classification theorist, but I found that classifying things rigorously is an extremely important task. In fact, it is one of the highest intellectual accomplishments that we can achieve if we can do those classifications rigorously. So, type definitions of entities, attributes and relationships form the basis for the standardization. So, we can move away from the empirical and ad hoc definitions to a formalism based upon these rigorous concepts in this. Now, with that, let me make a couple of remarks. So, we now have not only the human readable presentations of this complex tolerancing information, that is allowable variations, but carried in 3D models, so that in manufacturing you can control your processes so that you are within the specification. And you also have the compute machine readable representation. But what happens is that right from the early days, this type of information is also the governing document or a contract, legally binding contract between the designers and the manufacturers. And this is extremely important because not only within the same organization, within the same company, you need to have an unambiguous information exchange between the designers and manufacturers, particularly if you are going to subcontract this work, which is what is happening now. The global trade is based upon the fact that you do not have to co-locate all of them in one single place and force them to use the same language. You can have distributed resources now, and you can communicate this information unambiguously among these various participants is the key for global trade these days in that. So, this is a binding contract, but it is standardized so that there is no ambiguity associated with it. Now, what I found was that now in other domains, so far I have talked about variability in geometry or the spatial domain, but in this particular slide I showed you a work actually done by one of your colleagues from KTH and our friends at Berkeley, dealing with the inherent variability in the time domain. So, what they are thinking about is that there are these control engineers, control theory engineers, and these are the embedded software engineers. Timing is a very important issue, variability in the time is a very important issue in it. So, how can you come up with a common interface, an unambiguously interpretable interface, which is the basis for a contract between the control theory people and the embedded software engineering people? How can you come up with that? And this just started in the 2012 and there is some momentum towards this. I am very excited about it because we have been dealing with it in the geometry or the spatial domain, as I showed you, for centuries, and now we are beginning to address it in the time domain. And moving forward, it would be interesting to see whether we can address in a combined the space time domain, whether we can address this variability. Maybe there are some very interesting trade-offs that can optimize things much better rather than very strictly separating the geometry on the one side and dealing with the time on the other side. These are interesting ideas for us to pursue. Now, let me conclude with making a few remarks about the model based systems engineering, because that is a topic which has gained momentum in the last 5 to 10 years, and that is one of the areas in which KTH is also very much interested in it. So, the idea is, this is not my slide, this is a slide coming from INCOSE, that is the International Congress on Systems Engineering, which is a worldwide systems engineering practitioners society. And what they concluded is that for the 21st century, They want to move from document based practices to model based practices. In fact, they popularized the notion of model based systems engineering, and I give a lot of credit to them. There are lots of other thought leaders, including John Barras, who have been talking about model based systems engineering for a while, and it is nice that a big organization like Incosi recognized that. And in fact, when they came up with the Vision 2020 about 10 years ago, they made model based systems engineering as the basis for transformation. This is the major thing that we need to do in this particular field. Now, interesting, because when I heard that about 5 years ago, I thought that that's what we try to do in drawings. Remember, moving from the 2D drawings to 3D models that we have been doing for the last 30, 40 years. That's exactly what we were trying to do, and I immediately could relate to what these people are trying to do in the systems engineering, moving from documents to models. Now, what has happened is that the Vision 2020, as I told you, popularized the model based systems engineering, at least among the practitioners, as a very important thing to focus on. Now, just last year they published the Vision 2025 that you see here on the right hand side. So, they have updated their vision from 2020 to 2025. So, they are looking ahead for the next 10 years and seeing what they have to do. And what they have come up with, remember, these are the practitioners, these are not the academicians, these are the practitioners. What they have concluded is that they have to move from model based systems engineering to model based engineering. Now, why did they decide that they have to move from model based systems engineering to model based engineering? The reason is that they looked at the whole life cycle of a particular product. This is the life cycle management of a particular product, all the way from the initial requirements gathering to design, analysis, manufacturing and service. Look at the entire spectrum of the life cycle of a particular product in engineering. You can take any product in mind, whether it's a Volvo truck or a cell phone, whatever it is, you take anything in mind. They all have this life cycle aspect to them. And in every section of this life cycle, there are models. As I told you, for manufacturing, we have detailed geometric models, and I have not even talked about material models. There are a whole bunch of other models in it. And in the analysis, you have your finite element model, computational fluid dynamics models, and so on. And now, upfront in the systems engineering, if you develop models, remember, the models have some extra effort associated with it. You have to put in some extra effort to create these models. The overhead associated with creating the models is justifiable only if you know how to link the models in the systems engineering to models that are downstream in the design, analysis, manufacturing and so on. Otherwise, what do you do with the models that you have created upfront in that? Okay? Because we made a very good sale that we need to go to computerization, we need to have the rigor and so on. But now the practitioners are asking, how am I going to get the value out of these models? And that's why the shift from the vision is not to drop model based systems engineering. We have to do model based systems engineering, but we have to look at the entire model based engineering in order to derive the full benefit of it. That's why the workshop that Kale talked about in Lund next week is very timely. So, we need to look at both the model based systems engineering and the bigger picture of model based engineering to achieve the real purpose in this one. Now, let me conclude it with this observation on another slide. When I look at model based systems engineering, you know that there is a language called the SysML that helps us to build these models with the systems modeling language. The four major pillars of SysML are requirements, structure, behavior and parameters. And if you look very carefully into each of them, you will see that there are entities defined in these four pillars and also relationships defined in these four pillars. Just as I told you a few minutes ago that in geometry, people did come up with empirical classifications and definitions of the types, but it required a rigorous approach to prove the completeness or support these types of types and relationships to make further progress in this field. What would be interesting is to take a closer look at what many of the practitioners have come up with and see whether there is any formalism that we can have in this matter. In fact, if we can do that, that will be very helpful to put systems engineering in general and model based systems engineering in particular on a much stronger scientific footing. I think there is something there. We just have to sit down and then take a careful look at it. There are some portions of it where I see that things like Petri nets and bond graphs and so on can help, but some of us have got to sit down and then do a very thorough analysis of it and come up with the proper formalism in that. So, with that, let me have a summary of the journey that I have described so far. So, let me go back to the thesis slide that I put up at the beginning. So, I said that I would cover 3 topics in this. The first is that the models are critical to manufacturing, and you have seen right from the days of Plato, people have been thinking about models whenever they were making parts. So, it is true from the very beginning, and we have come a long way in 3D model based engineering for manufacturing, but we still have, I am not saying that we have reached the end of it, we still have a long way to go. Particularly if you think about the cognitive automation that the Vision 2030, Production 2030 had, we are nowhere near cognitive automation in that particular field, but that is the vision that people have for 2030, so we still have a long way to go. And finally, we can apply the lessons learned from the 3D model based engineering to other fields such as model based systems engineering, and we will continue this journey at Lund starting next week. So, with that, let me thank you for your attention, and Kale, if there is any time for Q&A, we can take it.
Yeah. Thank you very much. Thank you, Srini, for a very nice lecture, and thanks for teaching us something like about Platon and Euclid and Linnaeus. And so, time for questions. Who would like to start? Okay, the Greek.
So there's a very nice, thank you. So there's a very big challenge here, okay, from going to manufacturing to model-based system engineering and model-based engineering, and it has to do that the annotations now are extremely more complex because they have to deal with the different physics that are involved in the components, which can be represented by abstractions, as you correctly said, but then the logics of those abstractions will not be all geometric, they will be coming from physical laws. And one of the things we have hit in trying to get into modularity and compositionality is how do you go across different logics when you put together the assembly of these complex systems. Any thoughts about that?
The short answer is no, because we struggle with that too, as you know. Maybe in a way we were lucky in geometry because there are 2000 years plus knowledge that we can draw upon, and we can have formalism on that one. But I also would like to say that even though many of the things that I showed in geometry looked at annotations, they are much more than annotations. They are the inherent attributes associated with these entities, and they have a structure to them. And the whole emphasis on classification that I alluded to is to induce that particular structure to that what might seem like a random set of annotations. And that is where we spend most of our time, in figuring out the underlying classifications and the structure behind these annotations. So, the challenge would be in each of the fields that you mentioned, can we come up with an underlying classification or a structure for that particular information? If we can do that, we would have done a tremendous amount of service, not only for engineers to transfer information and so on, but to the whole field, because then we can base it and teach it from a much stronger scientific basis than some ad hoc set of practices, which is always very boring. But if you can come up with the scientific basis behind them, it is very exciting to teach it.
The linkage across the probabilities, if I follow you, it will be very much influenced by the domain experts or the set of domain experts. Like for instance, what do I do in buildings linking thermodynamics and heat flow and electronics versus what I do in airplanes? It may be different the way I link these constraints.
Exactly. The domain experts play a very important role. That is why I said that a cautionary note against the informatics hubris, because just because I know something about databases and classifications, it does not mean that I know how to classify things in every field.
So what about if we limit to dynamical systems? Because one way of interpreting when you talk about spatio-temporal systems and the separation about time and geometry, you make life easy, right, if you do like that. But if you now want to consider truly a dynamical system, it's not that
Exactly.
easy, right? So
Exactly.
do you have any thoughts about if we would go to dynamical models and classification of those, what that would correspond to in this setting?
Yeah, I think there is a very exciting field over there. And my humble opinion is that if we consider the space-time domain and get into the dynamics, and I already see how people are describing trajectories in the space-time domain for a lot of the dynamical system problems, maybe there are some very exciting opportunities, and that might have an impact on CPS. But it is still a speculative thought, because what people have done so far is, for practical reason, separate them out, so that they can handle this in one field and get it done right, and do this separately and get it done right. But the future might be to gain better performance out of these systems is to look at it in a more integrated way. And everywhere, this is one of the things that I try to tell people, is that the moment you enter into engineering, you cannot avoid variability. You have to discuss variability upfront. It is not an embarrassment that you try to deal with in the floor, but it is, you have to deal with it upfront, and you have to take it into account in the analysis, and you also have to do it in the design and control. In the contract that people write, they have to say not just the nominal value that I want, but what is the variability that I am willing to accept. And then the responsibility of the provider is to make sure that they are able to do that, and quite a lot of interactions among them, because knowing what is possible may alter the way in which you do the specification, which happens in manufacturing all the time, design and manufacturing all the time.
Thank you. Any further questions, comments? Let's check first. Okay, we give it to John again.
So I'll ask a question that goes very deep into mathematics. Okay, so one of the things we're struggling with in this composability goes beyond what you had to deal with in manufacturing in the following sense. In manufacturing, as you correctly point out with the jigs and everything, I had to worry about things fitting for a purpose, which was never explicitly written in the models. You have the annotations and so on and so forth, but it was never explicitly taken care, at least in my understanding in manufacturing, why I do the design, the geometric design in a certain way. I mean, although there were considerations of having fins for thermodynamic and all that stuff, right? This was hidden, and the major thing about fitting and geometric reasoning was the fitting and how can I reach my hand in the engine to repair it and so on and so forth. These were hidden. Now we go into this model-based system engineering, model-based engineering, where we want to explicitly do the following. We want to annotate metrics and performance metrics to the boxes, and we want to understand how these performance metrics compose from the components to the overall system.
Yeah.
One that people around here know very well is stability. Another one is energy efficiency, and so forth. And we find this is not easy unless the abstraction, as you correctly point out, has the right clustering and the right things in manufacturing. Is there anything that has happened in getting properties to compose?
Properties, no, but geometry, yes, because more and more you get the, in fact, in one of the slides that I showed you, on the left side, the entire assembly was there, the model of the assembly. And then one component was broken out, and its detailed specification was shown in one of the slides. So more and more people are actually doing the 3D models of the assemblies, which give you an idea, and not only that, they also, because now you have the tools, they give you the assembly instructions in 3D animation. How do you put these two things together? And the entire assembly sequencing is now a kind of a YouTube video. Okay, that's how they train the people in it. And in service, it is the reverse. How do you disassemble things to do the servicing in this? So now the PLM systems can do that with the full-fledged complex assemblies, how you put them together and then how you take them apart. And some of the examples that you refer to from the Iron Man movie picture, they are all now possible. You can do that in it. But other than the geometric things, the other things, the properties and so on that you are talking about, that is how these tolerances are going to influence the life of a bearing, because the bearing life depends upon some of the tightness of the fits and so on. That is all within the domain specific analysis and the expertise and the experimental results that they have gotten from that. We do not have it upfront as a model.